Welcome to Tech with Kaushik. This is set 12 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 12. Question number 204. This question checks your understanding of Lambda DB connection scaling. Scenario. A rapidly growing startup launched a serverless web application. The front-end uses Amazon CloudFront backed by an Amazon S3 bucket. The backend relies on Amazon API Gateway, several AWS Lambda functions written in Node.js, and an Amazon Aurora database cluster. The startup expects a massive, sudden spike in traffic due to a viral marketing campaign. A DevOps engineer conducts load testing and determines that while the architecture scales, the very first wave of requests suffers from severe latency. Profiling reveals that the Lambda functions are spending significant time initializing new database connections during cold starts, overwhelming the Aurora cluster with a sudden connection storm. Which combination of optimizations will resolve the initial latency and prevent the database connection storm? Choose 3. Identify all valid responses. Option A. Enable provision concurrency for the critical AWS Lambda functions to ensure execution environments are pre-warmed before the traffic spike. Option B. Implement Amazon RDS proxy between the Lambda functions and the Aurora database, and update the Lambda environment variables to point to the proxy endpoint. Option C. Refactor the Lambda function code to move the database connection initialization logic outside of the main function handler block. Option D. Configure a higher reserved concurrency limit for the critical AWS Lambda functions to guarantee they can scale up to the maximum expected burst limit. Option E. Refactor the Lambda function code to move the database connection initialization logic directly inside the main function handler block to ensure fresh connections. Option F. Migrate the Amazon Aurora database cluster to an Aurora global database and deploy red replicas in edge locations closest to the cloud front-edge caches. The required selections are Option A. Enable provision concurrency for the critical AWS Lambda functions to ensure execution environments are pre-warmed before the traffic spike. Option B. Implement Amazon RDS proxy between the Lambda functions and the Aurora database, and update the Lambda environment variables to point to the proxy endpoint. And Option C. Refactor the Lambda function code to move the database connection initialization logic outside of the main function handler block. Let's look at the reasoning. This scenario addresses a severe Lambda cold start and database connection exhaustion issue. Provision concurrency ensures Lambda functions are fully initialized and ready to execute immediately, drastically reducing cold start latency during the initial traffic spike. During the init phase, code placed outside the main handler block executes. By initializing the database connection globally, outside the handler, the connection is maintained across warm invocations, preventing the overhead of creating a new connection on every single request. Because thousands of concurrent Lambda instances might spin up, they can easily exceed the Aurora database's maximum connection limit. Amazon RDS proxy pools and multiplexes database connections, protecting the database from connection storms. D. Reserved concurrency limits the maximum scale a function can reach. It does not pre-warm environments and thus provides no protection against cold start latency. E. Moving connection logic inside the function handler forces the Lambda function to negotiate a brand new database connection on every single invocation, even warm ones, crippling performance. F. Aurora Global Database provides cross-region disaster recovery and low-latency global reads. It does not solve Lambda cold start issues or manage connection multiplexing for a sudden burst in a single region. Keep this point in mind for the exam. To solve Lambda database connection storms, combine 3 strategies. Initialize connections outside the handler, use provision concurrency, and route traffic through Amazon RDS proxy. Next, question number 205. A financial services company hosts a critical web application in East 1. The architecture spans multiple availability zones and consists of an application load balancer, containerized microservices on AWS Fargate, and an Amazon Aurora relational database. Infrastructure is defined in AWS CloudFormation, and Docker images are stored in Amazon ECR. Compliance requires disaster recovery in West 2 with an RPO of 8 hours and an RTO of 2 hours. Building Docker images from source takes approximately 3 hours. Disaster recovery testing shows that restoring an Aurora snapshot and deploying the CloudFormation stack with pre-built images can complete within 90 minutes. Which disaster recovery architecture meets both the RTO and RPO requirements while keeping idle infrastructure costs to an absolute minimum? Options. Option A. Store the CloudFormation templates in a location available from the disaster recovery region. Configure an AWS backup plan for the Aurora cluster with a backup frequency of no more than 8 hours and a cross-region copy rule to a backup vault in US, West 2. Enable Amazon EC or cross-region replication to US, West 2. During a disaster, restore the copied Aurora recovery point and deploy the CloudFormation stack using the replicated images. Option B. Replicate the CloudFormation templates and source code to an S3 bucket in the disaster recovery region. Enable AWS backup to take hourly cross-region snapshots of the Aurora database. During a disaster recovery event, build the Docker images from source in the disaster recovery region, push them to a new EC or repository, and deploy the CloudFormation stack using the restored database. Option C. Replicate the CloudFormation templates to an S3 bucket in the disaster recovery region. Pre-provision a dormant, identical CloudFormation stack in the disaster recovery region. Convert the Aurora database to an Aurora global database. When deploying new application versions, update the Fargate task definitions in both regions simultaneously to minimize disaster recovery failover time. Option D. Replicate the CloudFormation templates to an S3 bucket in the disaster recovery region. Schedule an Amazon Event Bridge rule in the primary region to invoke an AWS Lambda function hourly. The function creates an Aurora manual snapshot, exports the latest EC or image to a tarball, and copies both to the disaster recovery region S3 bucket for use during an emergency. The best choice is Option A. Store the CloudFormation templates in a location available from the disaster recovery region. Configure an AWS backup plan for the Aurora cluster with a backup frequency of no more than 8 hours and a cross-region copy rule to a backup vault in US, West 2. Enable Amazon EC or cross-region replication to US, West 2. During a disaster, restore the copied Aurora recovery point and deploy the CloudFormation stack using the replicated images. The main reason is this is a backup and restore design with minimal idle compute cost. AWS Backup supports scheduled cross-region copies for Aurora recovery points, so a backup interval no greater than 8 hours meets the RPO. EC or cross-region replication ensures the pre-built images are already in the disaster recovery region, avoiding the 3-hour image build that would violate the RTO. The stated tested restore and stack deployment time is within the 2-hour RTO. The other choices do not work because B. Rebuilding the container images during recovery takes about 3 hours by itself and therefore exceeds the 2-hour RTO. C. A pre-provisioned stack and Aurora global database reduce recovery time, but incur continuous standby cost, violating the absolute minimum idle cost requirement. D. Custom snapshot and image export Lambda automation duplicates managed AWS backup and EC are replication capabilities and adds operational risk. Here's a useful exam tip. Aurora does not support native RDS cross-region automated backup replication. For low-cost disaster recovery, use AWS backup cross-region copies and replicate any slow-to-build artifacts such as EC or images ahead of time. Question number 206. Let's go. We're moving on to CloudWatch Logs Insights. A security auditing application deployed on Amazon EC2 instances generates a text-based access log. Every time a user logs into the system, the application writes a line containing the username, timestamp, and source IP address. The application continuously streams this log file to a dedicated log group in Amazon CloudWatch Logs. On Tuesday afternoon, a security incident occurs. The incident response team urgently needs to determine the exact number of times a specific user, admin_do, successfully logged in over the preceding 7 days. No custom metrics were previously configured for this user. Which native CloudWatch capability allows the team to retrieve this historical count immediately? Choices. Option A. Open CloudWatch Logs Insights. Select the application's log group and execute a query utilizing the stats count aggregation function filtered by the username admin_do over a 7-day time range. Option B. Create a new CloudWatch Logs metric filter on the log group, specifying a filter pattern that matches the username admin_do. View the generated CloudWatch metric graph over the past 7 days to observe the total sum of logins. Option C. Configure a CloudWatch log subscription filter on the log group targeting an AWS Lambda function. Configure the Lambda function to scan historical log streams and output the total count for the username to an Amazon DynamoDB table. Option D. Create a CloudWatch custom dashboard. Add a specialized number widget and configure it with a real-time filter pattern for the username. Set the widget's historical evaluation window to 7 days to dynamically parse the logs. The answer here is option A. Open CloudWatch Logs Insights. Select the application's log group and execute a query utilizing the stats count aggregation function filtered by the username admin_do over a 7-day time range. Here's why. Amazon CloudWatch Logs Insights enables fast, interactive querying and analysis of log data in CloudWatch logs. It allows you to search historical data retrospectively without any prior configuration. Because the incident requires immediate analysis of the past 7 days and no metrics were configured in advance, writing an ad hoc query with stats count in Logs Insights is the only native, immediate solution. The remaining options can be eliminated because B. CloudWatch metric filters evaluate incoming log events after the filter is created. They cannot retrospectively scan historical logs to generate metrics for the past 7 days. C. Creating a subscription filter and a custom Lambda function to scan historical data is incredibly slow, complex, and unnecessary when Logs Insights provides an interactive query engine natively. D. CloudWatch dashboard widgets relying on filter patterns act identically to metric filters. They process real-time incoming data and cannot retroactively parse past logs dynamically without Logs Insights integration. The main takeaway is when you need to extract metrics or counts from CloudWatch logs retroactively, historical data analysis, and no metric filters were pre-configured, always rely on CloudWatch Logs Insights. Question number 207. Scenario. A DevOps team uses AWS Code Deploy to orchestrate in-place application updates to Amazon EC2 instances. The Code Deploy deployment group is configured to use a single tag group for instance identification. This single tag group currently lists 2 tags, environment equals production and name equals application A. Recently, a different team launched a new EC2 instance in the same AWS account. This new instance was tagged with department equals marketing, environment equals production, and name equals application B. During the next code deploy execution, the deployment mistakenly installed application A onto the marketing team's new instance. The DevOps team needs to restrict the deployment group so that application A is only installed on instances that have both the environment equals production tag and the name equals application A tag. How should the DevOps engineer reconfigure the deployment group tags to enforce this strict matching? Choices. Option A. Modify the deployment group to use 2 distinct tag groups. Place the environment equals production tag alone in the first tag group, and place the name equals application A tag alone in the second tag group. Option B. Keep the deployment configured with a single tag group, but update the tag list to explicitly include department equals marketing, environment equals production, and name equals application A. Option C. Modify the deployment group to use 2 distinct tag groups. Place environment equals production and name equals application A together in the first tag group, and place department equals marketing in the second tag group. Option D. Keep the deployment configured with a single tag group, but update the single tag group to contain only the environment equals production tag, relying on EC2 instance profiles to restrict the actual deployment access. The right response is option A. Modify the deployment group to use 2 distinct tag groups. Place the environment equals production tag alone in the first tag group, and place the name equals application A tag alone in the second tag group. In AWS Code Deploy, the way tags are grouped determines their logical evaluation. Tags placed within the same single tag group are evaluated as in or condition. The original setup matched instances that had environment equals production or name equals application A, which is why the marketing instance was mistakenly targeted. To enforce an and condition, you must place the tags into separate tag groups. Code Deploy evaluates distinct tag groups with an operator, ensuring the deployment only targets instances bearing both tags. Let's quickly check the incorrect choices. B. Adding department equals marketing into a single tag group expands the or condition further, increasing the blast radius rather than restricting it. C. Adding department equals marketing into a second tag group creates an and condition that requires instances to be tagged as marketing, which incorrectly targets the new instance rather than avoiding it. D. Relying on a single environment equals production tag removes the application name filter entirely, guaranteeing that the deployment will hit every production instance in the account regardless of its intended application. A helpful shortcut is this. In code deploy deployment groups, tags in the same tag group are treated as or. Tags in different tag groups are treated as and. Next, question number 208. A data analytics firm is an existing Amazon S3 Object Lambda customer that was using the service before November 7, 2025. It stores large amounts of raw, sensitive financial data in one S3 bucket. 3 internal applications need different views of the same objects. The raw data cannot be read directly by the applications. Each application requires different redaction logic to be applied dynamically as objects are retrieved, without storing 3 redacted copies. Which architecture meets these dynamic redaction requirements efficiently without duplicating data storage? Options. Option A. Create an S3 access point connected to the raw data bucket. For each of the 3 applications, create a distinct S3 Object Lambda access point attached to the S3 access point. Back each Object Lambda access point with an AWS Lambda function programmed with the application's specific redaction logic. Option B. Create 3 separate S3 buckets, one for each application. Configure S3 same region replication, SRR, to replicate objects from the raw bucket to the 3 application buckets. Configure an AWS Lambda trigger on each destination bucket to permanently redact the data upon object creation. Option C. Configure an Amazon Kinesis data stream. Deploy an AWS Lambda function triggered by S3 object created events in the raw bucket. Program the Lambda function to generate 3 differently redacted versions of the object and publish them to the stream for the applications to consume. Option D. Create 3 separate S3 access points directly on the raw data bucket. Attach an AWS Lambda event trigger to the S3 bucket that intercepts GetObject requests based on the requesting IAM role, redacts the payload, and returns the modified response directly through the standard access point. In this case, choose option A. Create an S3 access point connected to the raw data bucket. For each of the 3 applications, create a distinct S3 Object Lambda access point attached to the S3 access point. Back each Object Lambda access point with an AWS Lambda function programmed with the application's specific redaction logic. This is the best choice because for customers that remain eligible to use S3 Object Lambda, each Object Lambda access point can invoke a different Lambda function for the same underlying S3 data. That provides application-specific, on-the-fly transformation or redaction without duplicating stored objects. Here's why the alternatives are not suitable. B. Replication creates additional stored copies, and the redaction is no longer an on-demand transformation of the same raw object. C. S3 object-created events are ingestion-time events, not a mechanism for intercepting each application GetObject request. The design also creates multiple transformed payloads. D. Standard S3 access points do not invoke Lambda functions inline on GetObject responses. Exam tip. S3 Object Lambda remains available to customers already using it before November 7, 2025. New customers should use current alternatives such as invoking Lambda through CloudFront, API Gateway, or Function URLs. Question number 209. Let's go. This question takes us into proactive control enforcement. Scenario. A financial institution enforces strict governance across its multi-account cloud environment using AWS Control Tower and AWS CloudFormation. Security policies mandate that every single Amazon S3 bucket provisioned in the organization must be encrypted at rest using an AWS Key Management Service, AWS KMS, key. The cloud security team wants to prevent non-compliant S3 buckets from ever being created. If a developer submits a CloudFormation template that lacks KMS encryption for an S3 bucket, the deployment should be blocked proactively before the bucket resource is provisioned. Which mechanism will implement this preventative requirement? Option A. Utilize the AWS Control Tower multi-account environment to activate proactive controls on all relevant organizational units, OUs. Rely on the underlying AWS CloudFormation hooks deployed by Control Tower to inspect and block non-compliant bucket definitions. Option B. Create an AWS config organizational rule that continuously monitors for S3 buckets lacking KMS encryption. Deploy an AWS Organization Service Control Policy, SCP, to prevent developers from disabling or bypassing AWS config evaluations in their local accounts. Option C. Utilize the AWS Control Tower multi-account environment to activate detective controls on all relevant organizational units, OUs. Control Tower will automatically generate Amazon Event Bridge rules to terminate CloudFormation deployments that violate the policy. Option D. Deploy an AWS Organization Service Control Policy, SCP, to the organization root that explicitly denies the S3. Create bucket API action if the S3 XAML server-side encryption header does not equal AWS KMS. Go with option A. Utilize the AWS Control Tower multi-account environment to activate proactive controls on all relevant organizational units, OUs. Rely on the underlying AWS CloudFormation hooks deployed by Control Tower to inspect and block non-compliant bucket definitions. This works because AWS Control Tower offers three types of controls: preventative, SCPs, detective, AWS config, and proactive. Proactive controls evaluate resources before they are provisioned to ensure they comply with company policies. Control Tower implements proactive controls using AWS CloudFormation hooks. If a developer submits a CloudFormation stack to create an S3 bucket without KMS encryption, the hook evaluates the template pre-deployment and fails the stack creation proactively. Now let's rule out the other options. B. AWS config rules are detective controls. They evaluate resources after provisioning and cannot block a CloudFormation resource before creation. C. Detective controls do not terminate CloudFormation deployments pre-provisioning. Proactive controls provide that behavior through CloudFormation hooks. D. Default bucket encryption is configured through the S3 bucket encryption operation / CloudFormation bucket encryption property, not as an encryption header on the create bucket request. So this condition cannot reliably enforce the stated CloudFormation requirement. In AWS Control Tower, if a scenario requires blocking non-compliant resources before they are created via CloudFormation, always select proactive controls powered by AWS CloudFormation hooks. Question number 210. Scenario. A system administrator manages a large fleet of Linux-based Amazon EC2 instances residing in a single AWS account. The administrator uses AWS Systems Manager automation runbooks to execute monthly OS patching across the fleet. During the previous maintenance window, the patching automation failed on several instances. Root cause analysis determined that these specific instances ran out of disk space while downloading the large patch payloads, leaving them in a corrupted error state. The administrator wants to ensure that future patching operations fail safely and halt automatically if an instance lacks sufficient available disk space, preventing OS corruption. Which combination of actions should the administrator implement? Choose 2. Select all answers that apply. Choices. Option A. Install and configure the Amazon CloudWatch agent on all targeted EC2 instances to track and report internal disk space metrics. Option B. Define an Amazon CloudWatch alarm configured to trigger when available disk space drops below a critical threshold on the EC2 instances. Add this alarm as a safety control within the Systems Manager automation task configuration. Option C. Deploy a local cron job to all EC2 instances via user data that aggressively purges the /tmp directory every hour to guarantee disk space availability prior to patching. Option D. Create an AWS Lambda function that parses VPC flow logs to estimate disk input-output activity. Configure the Systems Manager automation runbook to invoke this Lambda function before initiating the patch installation step. Option E. Enable CloudWatch logs on all instances. Write a scheduled script on the instances that streams the output of the df-h command to a CloudWatch log stream, and trigger the patching automation only when the log confirms space is available. The correct answers are Option A. Install and configure the Amazon CloudWatch agent on all targeted EC2 instances to track and report internal disk space metrics, and Option B. Define an Amazon CloudWatch alarm configured to trigger when available disk space drops below a critical threshold on the EC2 instances. Add this alarm as a safety control within the Systems Manager automation task configuration. Let's look at the reasoning. By default, AWS CloudWatch only tracks hypervisor-level metrics like CPU and network input-output. To monitor internal OS metrics, such as available disk space, the Amazon CloudWatch agent must be installed on the instances A. Once disk metrics are flowing to CloudWatch, an alarm can be created. AWS Systems Manager Automation natively supports CloudWatch alarms as safety controls. By attaching the alarm to the automation runbook execution, B, Systems Manager will automatically monitor the alarm state. If disk space drops critically low during the operation, the alarm breaches, and Systems Manager safely halts the automation, preventing OS corruption. C. Aggressively deleting files and /tmp via a cron job is a dangerous, hacky workaround that risks deleting files actively used by the OS or the patching process itself. D. VPC flow logs capture network traffic data, IPs, ports. They cannot provide visibility into internal disk space utilization or input-output availability. E. Streaming DF/H text output into CloudWatch logs requires complex custom parsing to evaluate available space, whereas the CloudWatch agent natively structures this as a precise CloudWatch metric ready for alarming. Keep this point in mind for the exam. To use disk space or memory utilization as an automated safety control, you must install the CloudWatch agent to emit the metric and then integrate the resulting CloudWatch alarm into your deployment or automation framework. Question number 211. Let's go. The focus now shifts to our DS proxy with Lambda. A DevOps team maintains a serverless application consisting of Amazon Event Bridge rules that trigger an AWS Lambda function. The Lambda function runs read-only queries against an Amazon Aurora MySQL DB cluster. During peak operational hours, the Event Bridge rules invoke the Lambda function at a high concurrency rate. This causes the database to suffer from connection exhaustion, resulting in high latency and severely reduced database throughput. The team must optimize the architecture to handle the concurrent Lambda invocations without overwhelming the database. Which combination of steps should the DevOps team take to meet these requirements? Choose 3. Choose every option that satisfies the requirement. Option A. Refactor the Lambda function code so that the database connection is initialized outside the main event handler code block. Option B. Implement database connection pooling directly inside the Lambda execution environment by utilizing a software connection pool library. Option C. Create an Amazon RDS proxy for the Aurora cluster, configure an appropriate max connections % limit, and create a read-only proxy endpoint for the read workload. Option D. Update the Lambda function to connect directly to the underlying Aurora cluster endpoint instead of intermediate connection layers. E. Refactor the Lambda function code so that the database connection is explicitly opened and closed within the main event handler code block. F. Update the Lambda function to connect to the RDS proxy read-only endpoint. You should choose option A, refactor the Lambda function code so that the database connection is initialized outside the main event handler code block. Option C, create an Amazon RDS proxy for the Aurora cluster, configure an appropriate max connections % limit, and create a read-only proxy endpoint for the read workload. And option F, update the Lambda function to connect to the RDS proxy read-only endpoint. The main reason is initializing the database client or connection outside the handler allows a warm Lambda execution environment to reuse it across invocations. RDS proxy pools and multiplexes database connections and max connections % limits how many database connections the proxy can establish. For an Aurora read-only workload, a read-only proxy endpoint routes connections to Aurora reader instances, so Lambda should use that endpoint. The other choices do not work because B, an application-level pool inside each Lambda execution environment can improve local reuse, but high Lambda concurrency can still create many independent pools and connections. It does not replace the database-side protection provided by RDS proxy. D, connecting directly to the Aurora cluster bypasses RDS proxy and leaves the database exposed to connection bursts. E, opening and closing the connection inside every handler invocation increases connection churn and removes the benefit of warm environment connection reuse. Here's a useful exam tip. For Lambda to Aurora connection storms, use RDS proxy to protect database connections. For read-heavy Aurora workloads, use a read-only proxy endpoint. Next, question number 212. Scenario. A company operates a global application in 2 AWS regions. Application data is stored in an Amazon S3 bucket in the primary region, and two-way S3 cross-region replication is configured with a secondary region. S3 replication metrics and replication failure notifications are enabled. Occasionally, replication fails because of transient AWS KMS permission problems. A separate remediation restores the required KMS permissions. A DevOps engineer must reliably reprocess the objects whose replication status has failed, while absorbing bursts of failure notifications so the recovery logic is not overwhelmed. Which solution meets these requirements with the highest reliability? Options. Option A. Set up an Amazon Event Bridge rule that captures S3 failed replication events. Configure the rule to trigger an AWS Lambda function directly to download the failed object and upload it to the destination bucket. Option B. Send S3 replication operation failed replication notifications to an Amazon SQS standard queue. Configure AWS Lambda to consume the queue, collect the failed object identifiers into manifests, and submit S3 batch replication jobs after the KMS permissions are restored. Option C. Trigger an AWS Lambda function directly for every replication failure, and have each invocation immediately create a separate S3 batch replication job for the single failed object. Option D. Create an Amazon Event Bridge rule that captures S3 failed replication events. Configure the rule to trigger an Amazon SNS topic, which invokes an AWS Lambda function to immediately re-upload the object. The best choice is option B. Send S3 replication operation failed replication notifications to an Amazon SQS standard queue. Configure AWS Lambda to consume the queue, collect the failed object identifiers into manifests, and submit S3 batch replication jobs after the KMS permissions are restored. Here's why. A failed live S3 replication cannot simply be retried in place. AWS documents that failed objects must be uploaded again or replicated with S3 batch replication. S3 can emit operation failed replication notifications to SQS, which provides durable buffering during bursts. Lambda can then process the queued failures at a controlled rate and submit batch replication jobs after the underlying KMS permissions are corrected. The remaining options can be eliminated because A. Directly downloading and uploading the object creates a new application copy rather than retrying the failed S3 replication workflow, and direct Lambda invocation provides less buffering during bursts. C. S3 batch replication is the correct retry mechanism, but creating a separate job directly for every failure event has no durable queue to absorb bursts and creates unnecessary job management overhead. D. SNS can fan out notifications, but it does not provide the same consumer-side buffering and pacing as SQS, and re-uploading the object bypasses the intended replication retry mechanism. The main takeaway is when an S3 object has failed replication status, use S3 batch replication for retry. Use SQS when failure events can arrive in bursts. Question number 213. Let's go. An e-commerce platform is fronted by an Amazon Cloud Front distribution that routes traffic to a public application load balancer, ALB, in US, East 1. After a regional degradation, the business requires read-only HTTP GET requests to fail over without waiting for DNS health check detection or DNS cache expiration. The platform team has deployed a warm standby replica with a secondary ALB in US, West 2. A DevOps engineer must make CloudFront retry eligible requests against the secondary origin when the primary origin returns configured failure responses. Which solution provides the required application layer origin failover? Choices. Option A. Add the secondary ALB as a new origin to the CloudFront distribution. Create an origin group containing both ALBs, designating the primary ALB as the primary origin. Configure the origin group to fail over on HTTP 5XX errors, and assign this origin group to the default cache behavior. Option B. Deploy a second CloudFront distribution pointing to the secondary ALB. Use Amazon Route 53 with latency-based routing and active health checks to balance traffic between the two CloudFront distributions. Option C. Create an Amazon Route 53 alias record with a failover routing policy pointing to both ALBs. Set evaluate target health to yes with a TTL of 0. Update the CloudFront origin to point to this Route 53 record. Option D. Deploy a CloudFront function on the default cache behavior. Configure the function to inspect origin responses, detect HTTP 5xx errors, and return a 307 temporary redirect, instructing the client to query the secondary ALB. The answer here is option A. Add the secondary ALB as a new origin to the CloudFront distribution. Create an origin group containing both ALBs, designating the primary ALB as the primary origin. Configure the origin group to fail over on HTTP 5xx errors, and assign this origin group to the default cache behavior. CloudFront origin groups provide active-passive origin failover. For eligible methods such as get, head, and options, CloudFront can retry the request against the secondary origin when the primary origin returns one of the configured failover status codes, avoiding DNS-based failover propagation. Let's quickly check the incorrect choices. B. Two distributions with Route 53 health checks introduce health check detection and DNS resolution behavior instead of handling failover inside the existing CloudFront request. C. Route 53 failover is DNS-based and therefore depends on health check timing and resolver caching. It does not retry the current CloudFront origin request. D. CloudFront functions run on viewer request or viewer response events and are not a substitute for native origin group failover based on origin failure responses. A helpful shortcut is this. Use CloudFront origin groups when the requirement is request-level failover between origins without DNS failover delay. Question number 214. Next, let's move into organizations and SCPs. Scenario. A centralized cloud infrastructure team manages a multi-account environment using AWS organizations and AWS IAM Identity Center. A newly formed analytics group has been granted a dedicated AWS account. The analytics group requires administrator access to build their data pipelines. The infrastructure team has assigned them a custom permission set with the administrator access managed policy. However, security policies strictly dictate that the analytics group must be prevented from creating local IAM users in their account. Which solution provides the most robust enforcement of this security requirement? Option A. Create an IAM policy that explicitly allows all actions except the IAM. Create user action. Attach this policy as a permissions boundary to the permission set in IAM Identity Center. Option B. Create a service control policy, SCP, that includes an explicit deny for the IAM. Create user action. Attach this SCP directly to the analytics group's AWS account in AWS organizations. Option C. Create an IAM policy that includes an explicit deny for the IAM. Create user action. Attach this policy directly to the permission set in IAM Identity Center. Option D. Deploy an Amazon Event Bridge rule in the analytics account to detect the Create User AWS CloudTrail event. Configure the rule to trigger an AWS Lambda function that immediately deletes any newly created IAM user. Go with option B. Create a service control policy, SCP, that includes an explicit deny for the IAM. Create user action. Attach this SCP directly to the analytics group's AWS account in AWS organizations. This is the best choice because a service control policy, SCP, offers centralized control over the maximum available permissions for all accounts in an organization. An explicit deny in an SCP overrides any permissions granted by IAM identity-based policies, IAM Identity Center permission sets, or resource policies. Attaching the SCP ensures that no principal within the account, not even the root user or an administrator, can create local IAM users. Here's why the alternatives are not suitable. A. An IAM permissions boundary limits the maximum permissions of a specific IAM identity, but it can be bypassed if the user assumes a different role or if an administrator removes the boundary. SCPs operate at the account level and cannot be modified by account administrators. C. While an explicit deny on the permission set works for federated users using that set, it does not prevent an administrator from creating a role locally in the account that bypasses this restriction. D. A reactive event-driven deletion introduces a window of vulnerability where the newly created IAM user exists and could potentially be utilized before the Lambda function deletes it. Exam tip. Whenever a scenario requires absolute, unbypassable enforcement of a security rule across an entire AWS account, even for administrators, a service control policy, SCP, is the correct mechanism. Here comes question number 215. Consider this situation. An application uses an Amazon Kinesis data stream to aggregate application events. An AWS Lambda function processes these events and archives the transformed data into an Amazon S3 bucket. Currently, the Lambda function is the only consumer of the stream. The monitoring team has reported increasing end-to-end latency during peak event ingestion periods. A DevOps engineer is tasked with modifying the architecture to increase processing throughput and reduce latency. Which combination of configurations should the engineer apply? Choose 3. More than one answer may be correct. Review the options. Choice A. Register the Lambda function as a stream consumer with enhanced fanout enabled to provide a dedicated read throughput pipe. Choice B. Increase the batch size configured in the Lambda event source mapping to process more records per execution. Choice C. Increase the parallelization factor in the Lambda event source mapping to allow concurrent invocations per stream shard. Choice D. Disable the report batch item failures setting in the Lambda event source mapping to speed up batch processing. Choice E. Configure a reserved concurrency limit for the Lambda function to ensure it always has warm execution environments. Choice F. Split the existing shards in the Kinesis data stream to increase the total number of available shards. The answers that work here are option A. Register the Lambda function as a stream consumer with enhanced fanout enabled to provide a dedicated read throughput pipe. Option C. Increase the parallelization factor in the Lambda event source mapping to allow concurrent invocations per stream shard. And option F. Split the existing shards in the Kinesis data stream to increase the total number of available shards. This works because to reduce latency and increase throughput for Kinesis processing. 1. Splitting shards increases the overall capacity and parallel processing potential of the stream. 2. Increasing the parallelization factor allows Lambda to run up to 10 concurrent executions per shard, boosting throughput. 3. Enhanced fanout provides the consumer with its own dedicated read pipe, 2 megabytes/SEC per shard, eliminating contention and utilizing HTTP/2 for faster record delivery. Now let's rule out the other options. B. A larger batch can improve invocation efficiency, but it does not add shard read capacity or parallel processing lanes. Under shard saturation, it is not a reliable way to reduce iterator age by itself. D. Disabling report batch item failures forces the entire batch to fail and be retried if a single record fails, which significantly increases latency and reduces throughput. E. Reserve concurrency sets aside and caps concurrency for the function. It does not pre-initialize warm execution environments. Provisioned concurrency is the feature that pre-initializes environments. For Kinesis to Lambda backlog, scale the stream with more shards, increase parallelization factor when ordering requirements permit, and use enhanced fanout when dedicated low-latency consumer throughput is needed. Next up is question number 216. This is marked as a medium question. A rapidly growing enterprise manages dozens of AWS accounts across various business units using AWS organizations. Historically, each team manually implemented their own security baselines. The DevOps and security teams want to establish centralized, standardized governance. They require a solution that provides both preventive guardrails and detective controls across all existing accounts. Furthermore, the solution must automatically apply these identical controls whenever new accounts are provisioned in the future. Which approach meets these requirements with the least ongoing operational overhead? Option A. Use AWS organizations to create OUs for each team and attach service control policies, SCPs, to enforce preventive controls. Ensure all new accounts are manually placed in the correct OU upon creation. Option B. Set up a WS config in the management account to deploy configuration rules and remediation actions to all organization accounts. Manually enroll new accounts into the AWS config aggregator. Option C. Deploy an AWS control tower landing zone. Organize existing accounts into OUs within control tower. Enable the appropriate mandatory and strongly recommended controls, and provision all new accounts through Control Tower Account Factory. Option D. Use AWS Cloud Formation Stack sets from the management account to deploy IAM boundaries and AWS config conformance packs to the entire organization, scheduling a weekly sync to catch new accounts. The right response is Option C. Deploy an AWS Control Tower landing zone. Organize existing accounts into OUs within Control Tower. Enable the appropriate mandatory and strongly recommended controls, and provision all new accounts through Control Tower Account Factory. Let's look at the reasoning. AWS Control Tower provides the most operationally efficient way to set up and govern a secure, multi-account AWS environment. It automatically implements both preventive controls, using AWS Organizations SCPs, and detective controls, using AWS config rules, as managed guardrails. By provisioning new accounts through the Account Factory, Control Tower guarantees that these baselines are automatically and consistently applied without manual intervention. Using organizations with SCPs only provides preventive controls. It lacks the detective controls requested and requires manual processes to organize new accounts. AWS config provides detective controls but lacks preventive controls, like SCPs. Manually enrolling new accounts creates operational overhead and room for human error. While CloudFormation stack sets can deploy configurations, relying on a weekly sync leaves new accounts vulnerable and unmanaged between syncs, and managing complex guardrails via stack sets requires significant custom development overhead. Keep this point in mind for the exam. When a scenario demands automated provisioning, centralized governance, and a combination of preventive and detective guardrails with minimal operational overhead, AWS Control Tower is the target answer. Next, question number 217. A financial organization manages its AWS environment via AWS organizations, segmented into multiple organizational units, OUs. The company maintains several Amazon S3 buckets across different accounts that store sensitive audit reports. Currently, the S3 bucket resource policies restrict access strictly to the company's legacy on-premises IP address range. The networking team is migrating the corporate VPN to a new IP address range. A DevOps engineer must update the S3 configurations to allow the new IP range. Simultaneously, the security team requires that two specific OUs within the organization be completely denied access to these S3 buckets, regardless of their network location. Which solution accomplishes both goals effectively? Options. Option A. Create an SCP that allows access to the S3 buckets only if the request originates from the new IP range, and attach it to the root of the organization. Create a second SCP that explicitly denies access to the S3 buckets and attach it to the two restricted OUs. Option B. Update each S3 bucket policy to replace the legacy network restriction with a new corporate IP CIDR range, using an explicit deny for requests outside that range while excluding AWS service principals where appropriate. Create an SCP that explicitly denies access to these specific buckets and attach it to the two restricted OUs. Option C. Create a new SCP with two statements, one allowing S3 from the new IP range, and one denying access from the old IP range. Use a permissions boundary on the organization account access role in the two restricted OUs to prevent S3 access. Option D. Update the resource-based policies on all the relevant S3 buckets to allow access exclusively from the new IP address range. Update the IAM identity policies of all users in the two restricted OUs to explicitly deny S3 access. In this case, choose option B. Update each S3 bucket policy to replace the legacy network restriction with the new corporate IP CIDR range, using an explicit deny for requests outside that range while excluding AWS service principals where appropriate. Create an SCP that explicitly denies access to these specific buckets and attach it to the two restricted OUs. The main reason is the bucket policies are the resource-level control that enforces the corporate network boundary, so the legacy IP condition must be replaced with the new CIDR range. An explicit OU-level SCP deny then prevents principals in the two restricted OUs from accessing the specified buckets regardless of permissions they otherwise receive. When network context keys are used in deny policies, AWS service principal exceptions should be considered so legitimate service-to-service calls are not unintentionally blocked. The other choices do not work because SCPs do not grant access. An allow condition in an SCP cannot replace a bucket policy that still restricts access to the old IP range. C. An SCP allow does not grant S3 access, and a permissions boundary on one administrative role would not restrict every principal in the two OUs. D. Changing every identity policy is high overhead and incomplete because new roles or identities could bypass the intended OU-wide restriction. An SCP is the scalable preventive control. Here's a useful exam tip. Use the S3 bucket policy for resource/network restrictions and an SCP for organization-wide permission ceilings. Remember that SCPs never grant permissions. Question number 218. Here's the scenario. A DevOps engineer maintains an automated tagging utility using an AWS Lambda function. The function is designed to apply compliance tags to an AWS CloudFormation Stack instance. The organization requires that this Lambda function be invoked to apply the tags strictly after a stack has successfully completed an update operation. The CloudFormation Stack is currently configured to send all deployment events to an Amazon SNS topic, which implementation will trigger the tagging utility correctly with the least complexity. The choices are: Choice A, modify the CloudFormation Stack configuration so that it only emits update_complete events to the existing Amazon SNS topic. Subscribe the Lambda function directly to the SNS topic. Choice B, create an Amazon Event Bridge rule configured with an event pattern that matches the CloudFormation Stack status change event, where the status is update_complete. Set the Lambda function as the rule's target. Choice C, deploy a custom AWS config rule that triggers whenever a CloudFormation Stack changes state. Configure AWS config to directly invoke the Lambda function to remediate untagged stacks. Choice D, configure an AWS Systems Manager automation runbook that periodically polls the CloudFormation API for stacks in the update_complete state, and have the runbook invoke the Lambda function. The right response is option B. Create an Amazon Event Bridge rule configured with an event pattern that matches the CloudFormation Stack status change event, where the status is update_complete. Set the Lambda function as the rule's target. Here's why. Amazon Event Bridge natively receives state change events from AWS CloudFormation. By creating a rule with a specific event pattern matching its source, AWS, CloudFormation, and status details, status, update_complete. The Lambda function is invoked immediately and automatically only when a stack update succeeds, requiring no modifications to the CloudFormation stacks themselves. The remaining options can be eliminated because A, CloudFormation sends all stack events, for example, update_progress, update_complete, to a configured SNS topic. It does not have a native feature to filter only update_complete events before sending them to SNS, meaning the Lambda would be invoked unnecessarily for intermediate states. C, AWS config is a detective service that evaluates configuration state changes periodically or proactively, but it is not designed for immediate, event-driven execution of operational tasks like tagging upon stack completion. D, polling AP is via a scheduled systems manager automation runbook introduces unnecessary latency, violates event-driven best practices, and risks API throttling compared to the native Event Bridge integration. The main takeaway is for immediate, native responses to AWS resource state changes, like EC2 state, CloudFormation Stack status, or ECS task status. Amazon Event Bridge is the most efficient and standard solution. Next, question number 219. This question takes us into SQS Lambda DLQ batch failures. Scenario. A data processing pipeline relies on an Amazon SQS standard queue to buffer incoming payloads. An AWS Lambda function consumes messages from the queue with a batch size of 10. The function executes complex transformations and takes several seconds per batch. Recently, malformed payloads have been introduced into the queue. These payloads cause the Lambda function to throw exceptions, resulting in the entire batch failing and returning to the queue. As a result, valid messages are being continuously delayed, and the queue depth is growing uncontrollably. The team needs to ensure valid messages are processed promptly while isolating the malformed data. Which solution resolves this bottleneck with minimal architectural changes? Choices. Option A. Decrease the Lambda function's batch size to 1 to prevent invalid messages from failing valid ones. Increase the SQS maximum receive count to allow more processing attempts. Option B. Migrate the queue to an SQS FIFO queue to ensure strict ordering and configure a high concurrency limit on the Lambda function to power through the backlog. Option C. Maintain the current batch size. Update the Lambda handler to catch per message failures and return a partial batch response containing batch item failures. Enable report batch item failures on the event source mapping. and configure an SQS dead letter queue, DLQ, with an appropriate max receive count. Option D, maintain the current Lambda batch size. Configure an SQS dead letter queue, DLQ, and implement Amazon S3 transfer acceleration on the destination bucket to reduce processing time. The best choice is option C, maintain the current batch size. Update the Lambda handler to catch per message failures and return a partial batch response containing batch item failures. Enable report batch item failures on the event source mapping and configure an SQS dead letter queue, DLQ, with an appropriate max receive count. Lambda partial batch response requires both sides of the integration. The event source mapping must enable report batch item failures, and the function must return the identifiers of only the failed SQS records instead of throwing an exception for the whole batch. Successful messages can then be deleted while malformed messages are retried and eventually moved to the SQS DLQ after max receive count is reached. Let's quickly check the incorrect choices. A. Batch size 1 avoids mixed batches, but sacrifices batching efficiency and does not isolate poison messages as cleanly as partial batch responses plus a DLQ. B. FIFO ordering does not fix malformed payloads and can make a poison message block later messages in the same message group. D. A DLQ alone does not prevent valid messages in a failed batch from being retried when the function throws for the entire batch. Partial batch response logic is still required. A helpful shortcut is this. For Lambda with SQS batches, enable report batch item failures and implement batch item failures in the function. Pair it with an SQS redrive policy for poison messages. Now for question number 220. Here's what is happening. A heavily regulated enterprise uses AWS organizations to manage dozens of member accounts. Security policy requires human and workload principals in all member accounts to call AWS AP is only from registered corporate public IP CIDR blocks. Legitimate AWS service-to-service calls must continue to work. A security engineer needs a centralized preventive control for the member accounts. Which centralized approach enforces this requirement effectively? Here are the options. Option A. Create an AWS network firewall policy restricting source traffic to the corporate IP range and apply it to all accounts using AWS Firewall Manager. Option B. Create a trusted IP list in Amazon GuardDuty containing the corporate IP range and activate it for the entire organization via the delegated administrator account. Option C. Attach an SCP at the organization root with an explicit deny for requests whose AWS source IP is outside the corporate CIDR ranges and scope the deny so it does not apply when AWS principal of AWS service is true. Option D. Create a service control policy, SCP, at the organization root containing an allow effect for all actions exclusively when the AWS source IP condition matches the corporate IP range. The answer here is option C. Attach an SCP at the organization root with an explicit deny for requests whose AWS source IP is outside the corporate CIDR ranges and scope the deny so it does not apply when AWS principal of the AWS service is true. This is the best choice because an SCP attached at the organization root can cap permissions for principals in all member accounts. An explicit deny with not IP address on AWS source IP blocks calls from outside the corporate CIDRs, while excluding AWS service principals prevents network context redaction and service-to-service calls from causing unintended denials. SCPs affect member accounts, not the organization's management account, which is why the scenario is scoped accordingly. Here's why the alternatives are not suitable. A. AWS network firewall controls network traffic through VPC network paths. It is not an organization-wide authorization control for AWS API requests. B. GuardDuty trusted IP lists influence threat detection findings. They do not deny AWS API actions. D. An allow statement is not a reliable deny guardrail when broader allow SCPs, such as full AWS access, remain attached. An explicit conditional deny is the robust preventive pattern. Exam tip. SCPs can restrict AWS API permissions in member accounts. For AWS source IP deny guardrails account for AWS service principals, so service-to-service calls are not accidentally blocked. Question number 221. Let's go. The focus now shifts to S3 batch and replication. A media company relies on an Amazon S3 bucket in the US, East, one region to host assets. To improve disaster recovery capabilities, a DevOps engineer is implementing an active-passive multi-region architecture and has created a new target S3 bucket in the EU, West, one region. The solution requires that all existing assets in the primary bucket be copied to the new secondary bucket. Furthermore, the application must be able to fail over to the secondary region and fail back seamlessly, meaning any new objects or updates must be continuously synchronized between the two buckets going forward without data loss. Which combination of steps achieves these requirements with the most operational efficiency? Choose 3. Identify all valid responses. Option A. Configure S3 replication in both directions by creating a replication rule on the primary bucket that targets the secondary bucket and a corresponding rule on the secondary bucket that targets the primary bucket. Enable replica modification sync if replicated metadata changes must also synchronize. Option B. Create an S3 cross-region replication (CRR) rule exclusively on the source S3 bucket to continuously push updates to the target bucket. Option C. Provision an AWS Fargate task using AWS batch to run an AWS S3 sync command on a scheduled cron to synchronize the existing assets. Option D. Create an S3 batch operations replication job targeting the primary S3 bucket to retroactively replicate all existing contents to the secondary bucket. Option E. Create the IAM roles and policies required for the live S3 replication rules and for the S3 batch replication job, with the appropriate S3 and S3 batch operations service trust and object permissions. Option F. Create an IAM role explicitly trusting the AWS batch service principal, providing it full read/write access to both S3 buckets. The answers that work here are Option A. Configure S3 replication in both directions by creating a replication rule on the primary bucket that targets the secondary bucket and a corresponding rule on the secondary bucket that targets the primary bucket. Enable replica modification sync if replicated metadata changes must also synchronize. Option D. Create an S3 batch operations replication job targeting the primary S3 bucket to retroactively replicate all existing contents to the secondary bucket. And Option E. Create the IAM roles and policies required for the live S3 replication rules and for the S3 batch replication job, with the appropriate S3 and S3 batch operations service trust and object permissions. This works because bidirectional replication requires a replication rule in each direction so new writes made after failover can flow back to the other bucket. Existing objects are not retroactively handled by ordinary live replication rules, so S3 batch replication is the native mechanism to replicate the pre-existing inventory. The replication workflows also need service roles with the required source, destination, and KMS permissions as applicable. Now let's rule out the other options. B. One-way CRR does not synchronize writes made to the secondary bucket back to the primary bucket during failover, so failback can lose changes. C. A scheduled AWS S3 sync job adds custom compute and scheduling overhead and does not provide the native replication semantics of S3 replication and batch replication. F. AWS batch is a container compute scheduler and is not the service principal used by S3 batch operations replication jobs. Use a replication rule in each direction for bidirectional S3 replication, and use S3 batch replication to seed or retry objects that live replication did not process. You have completed Set 12 of the DOP-C02, AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.